For years, astronomers have been puzzled by the unusual orbits of giant planets found in other solar systems. Unlike Jupiter and Saturn, which move in nearly perfect circles around the Sun, many of these exoplanets follow stretched-out, eccentric orbits. Even more puzzling is the existence of hot Jupiters, gas giants that orbit extremely close to their stars. Scientists have been searching for an explanation, and a new study may have just found it. The study, led by Grant Weldon and colleagues at UCLA, suggests that a process called the Eccentric Kozai-Lidov mechanism, or EKL, which involves gravitational interactions with a distant companion star, could explain why some giant planets develop eccentric orbits while others become hot Jupiters. In our solar system, giant planets like Jupiter and Saturn orbit in neat, nearly circular paths. But when astronomers began discovering exoplanets, they found that many of them had wildly eccentric orbits, meaning they follow stretched-out paths rather than circles. Some of these planets come dangerously close to their stars before swinging far out into space. A different category of exoplanets, known as hot Jupiters, orbit extremely close to their stars, completing a full orbit in just a few days. According to what we know about planet formation, these gas giants should have formed much farther away. So how did they end up in such extreme locations? Scientists have proposed several ideas to explain these phenomena, including gravitational interactions between planets, chaotic movements in the early solar system, and the influence of faraway stars. The new study focuses on the role of stellar companions, nearby stars that could be influencing the orbits of gas giants through gravity. The eccentric Kozai-Lidov mechanism occurs when a giant planet orbits its star while also feeling the gravitational pull of a distant companion star. This can cause the planet's orbit to tilt and stretch over time, increasing its eccentricity. Scientists previously thought this effect couldn't fully explain the orbits of cold Jupiters, planets that remain far from their stars, because earlier models assumed that planets always started on perfectly circular orbits. However, Weldon's team discovered that if planets begin with even slightly elliptical orbits, the EKL mechanism becomes much more effective. By running advanced computer simulations, they found that planets exposed to this process can end up with orbits almost identical to those observed in real exoplanet systems. This discovery has major implications for how we understand planetary system evolution. It suggests that many of the cold Jupiters we see today may have gone through intense gravitational interactions in their past. It also strengthens the idea that hot Jupiters may have started as cold Jupiters, only to be pushed into extreme, star-hugging orbits by the EKL mechanism. Additionally, the study explains why multiplanet systems tend to have more stable orbits. The researchers found that when a giant planet has planetary companions, these companions prevent extreme changes in its orbit, effectively stopping the EKL process. This could explain why we don't see many highly eccentric orbits in planetary systems with multiple gas giants. These findings offer a new perspective on how planetary systems evolve, but there's still more work to do. Astronomers plan to continue searching for binary star systems with exoplanets, looking for evidence that the EKL mechanism is shaping their orbits. Space telescopes like the James Webb Space Telescope and the upcoming Roman Space Telescope will provide even more data to test these ideas. This research brings us one step closer to understanding how planets move, migrate, and evolve, and perhaps, how our own solar system avoided such dramatic changes. Thanks for watching. If you enjoyed the video, give us a like, comment, and subscribe. And don't forget to click the bell icon to stay updated on the latest space discoveries.